Okay, I'm going to define a very, very crucial notion in group theory called homomorphism. Absolutely crucial. You see homomorphisms throughout group theory, and they are the one indispensable tool in understanding groups. I've got G and H, which are both groups, and I've got a map alpha which maps G to H, so it's a map from G to H, and I'm going to use this map alpha to try and understand the relationship between G and H. If that's all we had, then we wouldn't be any further forward, because I could put any stupid old map and yeah, we wouldn't be any further far forward. So I'm just going to make one restriction on alpha, and this is the definition of a homomorphism. So alpha is a homomorphism. You sometimes write HMism like that, if it's got the following property. X and Y are in G implies alpha of X, alpha of Y equals alpha of X, Y. At least that's what you see in the textbooks. It confused the living daylights out of me for years on end. So I'm going to spend a little bit of time unpacking this. This is what you see in the textbooks. The books give this, and then just leave you to flounder. But I'm going to take you through it in excruciating detail. You'll remember that I just used G as a shorthand for a group. I'm going to say G circle. You'll remember that a group is an ordered pair of a set and an operation, and I'm going to write H star. Not a very neat star, but there it is. So there's my set and there's my operation. So when I write, I'm just going to write this one out. Alpha of X, alpha of Y equals alpha of X, Y. If we start thinking about what these actually are, this guy here is actually a member of set H, and this guy here is actually a member of set H as well, because X and Y are in G. And alpha is a map which maps from G to H. So if you give it something, if you give the map alpha something in G, it spits back, it gives back, it returns something in H. So, and I've just casually written them together. What I really mean is this: alpha of X, because it's a member of H, I've got to use the star to combine it with alpha Y, because star is something that takes elements of H, and that equals alpha of X, and this has got to be a little circle here, because here we've got two elements of G which are multiplied together, and the group operation for G, I'm using a circle. X star alpha Y, this is the group operation of H, equals alpha of X composed with the composition of G of Y. And that is the definition of a homomorphism. It's somewhat astonishing to me that you can get so much insight and so much group theory out of such a simple definition. When I was doing my revision, I remember thinking, I can't believe you get so much stuff out of a homomorphism. But you do, and this is what it is. So I'm going to go back to what the textbooks give you. I'm going to go back to this. But you've always got to bear in mind, well, what exactly is being mapped here? What exactly is the map? And the map here is the map in H, and the map here is the map in G. Okay? But that's what it really means. That's the real deal. And I'm going to stop there.